Okay, so last time we left off, we were discussing electrophilic aromatic substitution reactions, and we've been drawing mechanisms for a range of electrophilic aromatic substitution reactions. And it's really important to think critically about the reaction conditions in your substrate when you're drawing a mechanism and when you're proposing products for a reaction. So when we have the following reactions, let's take a moment and let's continue to practice drawing mechanisms. And let's work on the following two examples as sort of our starter examples for today's class session. So I'd ask us to try and draw a mechanism for the following reactions, if applicable, and to predict the products, if any, for this reaction. So let's take about 3 to 4 minutes to work on these examples. And I'd like to see students propose responses in the chat or verbally. What products, if any, do we get from the following reactions? And what do we observe from these reaction conditions? Does that make sense? So what does the class think? Does anyone have some proposed comments on these reaction conditions? What products do we observe, if any? So I'd like to see a few comments in the chat or verbally or using the annotate tool to share your comments. So we have one student commenting that this acetyl group is an electron withdrawing group. That's important to note. And under these current conditions, we're looking at Friedel-Crafts acylation conditions. My question to everyone then becomes, does this reaction occur? So if you have a deactivated ring, does the Friedel-Crafts acylation reaction proceed? No. So this first case would be no reaction. Yep. So in this second case, we have a free amine and we're running a reaction under Friedel-Crafts alkylation conditions. So what do we think about these conditions and these functional groups? If we think about our previous discussions for the Friedel-Crafts reaction, what can we conclude from these conditions? What does the class think? Or to phrase it another way, so the amine is an electron donor, yes, but it's an incompatible functional group. As we discussed when we talked about the Friedel-Crafts reaction, when we have a free amine or an amine with an available lone pair, this free amine can readily coordinate our Lewis acid catalyst, or the free amine can react with our electrophile at the nitrogen site. Coordination is more common as that deactivates the ring. And essentially your reaction's done then and there because you've coordinated your nitrogen lone pair. And as a result, you're not really able to see any further reaction. Coordination of the nitrogen lone pair deactivates the ring, so that stalls the reaction. And further, the nitrogen lone pair itself could just as easily go on and react with our electrophile under the conditions. So a free amine is an incompatible functional group. And under the reaction conditions, the amine interferes with the reaction and in turn prevents full reaction via Friedel-Crafts alkylation from occurring. Does this idea of incompatible functional groups seem familiar? When we discussed the Friedel-Crafts alkylation, we discussed incompatible conditions and functional groups. And it's always important when you look at a reaction condition, you consider whether the ring is activated or deactivated, and sort of what are the consequences of having this functional group in your molecule under these reaction conditions. Does that make sense? Does this idea make sense? Okay, perfect. So let's talk about what happens when we have multiple substituent effects and we're trying to generate tri-substituted benzenes. So in this case, if the directing effects of the two groups are identical, then the result is additive. So for example, if you have a methyl group, which is an ortho para director, so the methyl group is going to direct to the ortho positions. And your nitro group, which is a meta director, is going to direct to the meta positions relative to the nitro group. As you notice, both of our directing effects are activating the ring for and promoting reaction at the following positions. So when we try to brominate paranitrotoluene, we will see installation of our bromine exclusively at the 2 position relative to our methyl group. So it's ortho to our methyl group and meta to the nitro group. So does everyone see how the 2 directing effects are directing to the same position, and as such it's an additive effect?
Professor, does it matter like which side it's going to be added in?
So looking at the alternative structure, is this structure the same or different? So are the 2 positions identical or different?
They're the same.
Yep, they're the same. But it is an important point to bring up, since there are cases where the 2 ortho positions are non-equivalent, as we'll see in a moment. But it's always important to ask. But in this case, both the ortho positions are identical, or they're degenerate, and they lead to the same product. Does that answer your question?
Yes, it does. Thank you.
Perfect. Okay, so let's keep going then. So sometimes you end up with substituents with opposite effects. So if the directing effects of 2 groups oppose each other, then the more powerful activating group decides the principal outcome. You'll still get a mixture, but the mixture will be biased towards the position with that's the position activated by your strongest directing group. So for example, the methyl and hydroxyl are both ortho-para activators, but the hydroxyl group is a more powerful activator than a methyl group. Generally, resonance donors and withdrawing groups are stronger directing groups. So for example, you have this push-pull dynamic. Your hydroxyl group, which is a pi donor or a resonance donor, activates at the ortho positions relative to the hydroxy group. The methyl group is a weaker sigma donor, and as a result, it has a weaker activating effect. So when you subject this substrate, paramethylphenol, to electrophilic aromatic nitration conditions, you install your nitro group preferentially at the ortho position relative to your stronger activating group, which is your hydroxyl group. Does that idea make sense? Stronger directing groups have preference for their directing effects. And in turn, pi donors, resonance donors, and acceptors are stronger directing groups than sigma donors and acceptors in most cases.
Professor, I have a question.
Yes?
So for the alcohol ones or the hydroxyl, sorry, since it's stronger, is it automatically a pi donor, or does it matter in the?
It's more. It is a pi donor. As a result, it's a stronger director.
Oh, okay. And
While
since,
sigma donors are generally weaker directors.
oh, okay, got it. Okay,
Does
thank
that
you.
make sense?
Yes. Thank
Perfect. Of course, you do still see a mixture, but it's heavily biased towards the position that's most activated by your directing groups. So for example, you will get a little bit of the alternative product, and your alternative product in this case would look like what? So we have our benzene ring. What would the other product look like for this reaction?
Would it be like at the bottom or the what is it, the methyl?
Exactly right. So the other possible product would be from direction of the methyl group to the ortho position, and you end up with the nitro group at the 3 position relative to your hydroxyl group. Yep, exactly right. So this is the minor product. So you should be able to draw major and minor products. Any other questions on this example?
Oh, another question. If we were to see, whenever we see the, oh my gosh, the hydroxyl and the methyl will automatically know that the hydroxyl is a stronger, so we're gonna get that major one that we
Yes.
had at the top.
Yes.
And if it was
Yes.
like 2 ethyls, like one ethyl at the bottom and one ethyl at the top, or one methyl at the bottom and one methyl at the top,
Then they'd be identical.
they'd be identical.
Yeah, because
What's
the product would be identical.
Oh.
What I think you're getting at is an issue if we have 2 groups that are different, but both pi donors or both sigma donors, and they're directing to different positions. And we'll actually talk about that in a moment. And
Okay.
we'll talk about the deciding factor. And to help us understand the rationale when we have identical directing groups, let's talk a little bit about meta-disubstituted compounds. And these are a classic case where you often can have 2 directing groups pointing in opposite locations. So a central theme of these meta-disubstituted compounds is this idea of hindrance and sterics serving as another factor. So this methyl group is an ortho-para director. It directs to the ortho positions and the para positions. The chlorine, interestingly enough, is an ortho-para director, and it's deactivating, and it directs to the ortho and para positions. Now, one thing that's universal for these meta-disubstituted compounds is that the position in between both of your substituents, this position here is highly hindered. This is very hindered. And as a result, it's very difficult for you to see reaction and installation of your functional group ortho to both of your substituents. You will overwhelmingly see reaction primarily para to one of your two substituents. You will never see installation of your functional group typically between your two substituents. So in this case, there's no meta product that's observed. And in terms of the ratio between the 3,4-dichlorotoluene and 2,5-dichlorotoluene, I'd say they're very close. This is slightly major, but not by much. It's almost 50-50, I'd say. The main point that I'm trying to make here is we have directing effects directing to the same positions. However, the position in between our two substituents, this ortho position in between our two substituents, is not very reactive. It's so hindered that we prefer to install our functional group at the other positions. We will never see this 2,3-dichlorotoluene. We don't observe any of it. And that's due to steric hindrance, making this product very difficult to generate. Does that idea make sense? The idea that sterics can influence our regioselectivity. And for meta-disubstituted compounds, we're almost always going to see reaction at positions other than the ortho position between our two substituents. Does that answer your question? Did that clarify? Okay, perfect. So continuing on from there, when we talk a little bit about ways to get around this, an easier workaround is to start with the 1,2 disubstituted product or the ortho disubstituted product. So if you start from orthonitrotoluene, again, your methyl directs ortho, your nitro group directs meta, you have a synergistic effect, well, ortho para and then meta. You have a synergistic effect, you're activating this ortho and para position relative to your methyl group, and it allows you to cleanly generate this tri-substituted aromatic ring. So if you want to make an aromatic ring with 3 adjacent substituents, it's best to start from the ortho disubstituted compound. Does everyone see how the issue of sterics is not as pronounced in this case? Because we're never installing a substituent between 2 of our groups already present on the ring. Does that idea make sense to everyone?
Wait, so since I'm assuming it's the chlorine wasn't placed in between the methyl and the whatever, the nitro.
Yep. Mm-hmm.
That's no steric, is what you're saying?
Or we have less issues with steric strain, because when we start from the ortho disubstituted compound, you're not trying to place your substituent between 2 bulky groups already present in your ring. You're installing your substituent adjacent to another substituent in the ring. And as a result, you pay less of a steric penalty. And as a result, it's easier to install that functional group via electrophilic aromatic substitution.
Did you circle the 3 adjacent substituted thing as saying it's major, or just?
No, I'm just saying that it's possible to form this compound. Well, in the previous cases, when we started from the meta disubstituted compound, we could not generate it.
Okay.
It's due to
Thank
the
you.
steric hindrance and the penalty that you pay that in turn leads to the 2,5 disubstituted and the 3,4 disubstituted products being major. So essentially, if you want to make a tri-substituted aromatic ring with 3 adjacent substituents, you need to start from the ortho-disubstituted compound. Otherwise, you'll never be able to install your last substituent due to steric hindrance. Does that idea make sense?
Yes. Thank you.
Perfect. Did I address the question in the chat as well?
Professor, I have a question.
Sure, please go ahead.
So is the 2-chloro-6-nitrotoluene the ortho substituted product?
Yeah, you could say that it's ortho substituted relative to the methyl group.
Okay, relative to the methyl. Okay.
Yeah, while the 4-fluoro is para relative to the methyl group.
Oh, okay, that makes a lot more sense now looking at it that way.
Does that
Thank
idea
you.
make sense? Perfect.
Yeah. Thank you.
Any other questions that I can address?
Yes, I actually have another one. So we chose to start with the methyl as our number 1 versus the nitro.
Yep, and it's perfect. Let me rephrase this. It's arbitrary in a sense that you can pick any substituent to be at locant 1. However, because this is named as toluene, and toluene is our base ring, the methyl as part of our base ring, the methyl as part of this toluene base is inherently assigned carbon number 1.
Okay, that makes
Does that make sense?
Yes, thank you so much.
Okay, perfect. Any other questions I can address? Okay, so let's keep going then. And let's talk about some noteworthy steric effects. So similar to this idea that steric effects play a pretty big role in regioselectivity, the para position is inherently preferred over the ortho position to minimize steric hindrance. So this isopropyl group takes up space. And as a result, we prefer to install our new functional group as far away as possible from our bulky, sterically hindered isopropyl group. That's why our para product is major and the ortho product is minor. We're still dealing with directing effects here. We're still dealing with fundamentally this isopropyl group still is an ortho para director. However, if we have a choice between the ortho and para position, the para position is preferred to minimize steric hindrance. Does that idea make sense? Perfect. So, in cases where you have 2 substituents that are both, in this case, we have 2 sigma donors, and so we have ortho-para directing effects. This is the example one of the students brought up that they wanted a little more clarification on. So in cases where you have identical directing effects, and it's a 1,4 disubstituted ring, so this isopropyl group is directing to its 2 ortho positions, the methyl group is directing to the 2 ortho positions. They're equally strong directing groups, so we can't break the tie there. However, isopropyl is very hindered. And as a result, if we have a choice, we want to place the nitro group as far away from this hindered group. And that's why, as a result, the ortho product relative to the methyl is major, while the ortho product relative to the isopropyl group is minor. And that's simply due to steric strain. So does everyone get how sterics can impact regioselectivity? So in cases where you have equal directing effects, the least hindered product will generally be preferred. Any other questions on this example? Okay, so let's keep going then. And I'll do the first example and you'll do the second two. So in this case, we're asked to predict the product from the following reaction. So we have iron tribromide and bromine. These are electrophilic aromatic bromination conditions. I'm going to look at each of my substituents. The hydroxyl group is an ortho-para director and it's a pi donor. The nitro group is a pi acceptor and a meta director. Okay. Well, there's only one meta position, so here we go. The hydroxyl group is an ortho-para director, so it directs here. And the methyl group is a sigma donor, so I'm going to draw it with a little bit of a weaker arrow. It's not as strong of a director. So in cases where we have multiple substituents, we first look for additive effects. So two of our very strong directing groups are pointing to the same position. And in terms of directing effects, the pi donor and pi acceptor groups are stronger directing groups. Thus, we will see exclusive reaction at the ortho position. And so we will install our bromine ortho relative to the hydroxyl group or the alcohol. And again, this is based on this idea that when we generate our carbocation, so if we generate a carbocation, that carbocation formed via substitution at this position is stabilized via resonance, and it is never destabilized directly by your electron withdrawing nitro group. So everything can be traced back to this idea of carbocation stability. Does this first example make sense to everyone?
Is the first product going to be major?
Yes. I mean, it's overwhelmingly major. The other two possible products with bromination, well, there are two other possible products to consider, but they're very minor. And we can talk about them for sure. Let's draw them in a different color. So which product of the other possible options remaining would be the next most major? What's the, I know this is a bit of a contradiction. What is the major minor product? What is the most abundant minor product that we would see? So would we see reaction at position 1 or 2? I'm just arbitrarily labeling them 1 and 2. Which position would we see more reactivity at?
Is it number 2?
Number 2, yes. And would you be able to provide an explanation for why? Why is this position preferred?
Is it because of the para positioning and it kind of balances it out?
Para position, yes, it is directed. Yep, that is true. If we tried to install a substituent at this ortho position, there's a steric issue. Remember, when we have meta disubstituted compounds, generally it's very hard to install a functional group in between your two substituents. So you don't see this bromination product due to sterics. Does that idea make sense? Does this first example make sense?
Yes, thank you.
Okay, so let's take a look at the following two examples, and let's try to draw and predict the products for these two reactions. And don't be shy to share your responses as a photo in the chat. Oh, I'm noticing a little bit of background. Give me one moment. And if you have a question, don't be shy to unmute. There's a table earlier on in the notes. Generally ortho-para directors are sigma donors or pi donors. So they're electron-rich donating groups, while meta-directing groups are pi acceptors or sigma acceptors. So meta-directing groups are generally electron withdrawing. And that's based on this idea that you're either stabilizing or selectively destabilizing certain carbocation intermediates. So with that established, let's take a look at these two examples and let's try to predict the product. You can share your responses using the annotate tool as part of Zoom, or you can share a screenshot of your work in the chat. And you can also share your proposed responses verbally as well. I guess what we can do is we can label these positions. I'm just giving them arbitrary numbers, so we're not using the IUPAC numbers. I'm just labeling these positions with arbitrary numbers for problem A and B, just so that way if the class would like to share their opinion in terms of which positions will we see substitution and what group will we install in those positions, I'd like to see your responses in the chat, and this helps facilitate that. So let's keep working on this example. Ideally, we'd have someone annotate their proposed product. And we'll go from there. We'll spend about 4 to 5 minutes on this example. So deactivators, so we consider deactivating groups in terms of overall, if you look at all the activating and deactivating groups, do you have a net activated or deactivated ring? This is only really important when you're dealing with Friedel-Crafts reactions and you're concerned whether or not your withdrawing group is going to halt the ring from reacting entirely or deactivate the ring from reacting entirely. You do have to consider how each of the directing effects add together, and by adding up each of your directing effects, you can in turn figure out the regioselectivity. Does that answer your question? So the first ring has a strong deactivator, a strong activator, and a deactivating group. And sort of the best way I like to approach this is by drawing arrows. And you may have a mixture. There may be a mixture. And part of your goal is to sort of weigh, how do these effects compare? Is there a set of directing effects that are going to lead to a major product? Is there a set of directing effects that will lead to a minor product? Are we going to see a mixture? And that's part of what this question is trying to help showcase. So we have the arrows drawn. It looks like the student is slowly arriving at a conclusion. We have some students commenting in the chat that reaction at positions 2 and 3 look pretty major. They're saying that product 3 was major while product 2 is minor. Let's see what the student who's annotating draws out, as it looks like he's drawing out the structures that match that conclusion. One thing, just be careful with how you draw your double bonds. Make sure they're drawn accurately, just so that way they're clearly showing we have an aromatic ring. Yep, perfect. Now let's add our substituents on and let's indicate the major and minor product. And interestingly enough, there are only 2 products observed in this reaction. The third product is never seen, interestingly. So we have the first product drawn, which is reaction at position 3, arbitrarily labeled, and they call this major because it has both of your directing groups directing reaction at that position. Two is minor. Yep, that's correctly noted. Okay. And interestingly enough, position number 1 doesn't react. So let's talk about why that is. And let me clear the annotations. But these proposed responses look great. So let's draw this out. So first things first, our amine is an ortho para director and it's activating. So it's going to direct at the following ortho positions. I'm going to erase these numbers now. Okay. The fluorine, it's deactivating, but it's an ortho para director. And the nitro group is a meta director. So adding up our directing effects, we see that the position that is ortho to our fluorine would be major. Under these conditions, we're dealing with electrophilic aromatic iodination. So we're installing an iodine substituent. And so this would be the following major product. The second, I wouldn't call it minor only in the sense that there's a little bit less of it, but this second product, the ortho position to the amine is also pretty heavily activated. So I'd say this would also be the second major product. Interestingly enough, we observe none, functionally none, of the third possible product option. And again, would someone care to offer a reason why do we not see this third product? Why do we not see this third product?
It's in between 2
Yep.
substituents.
Yep. And what's the driving force? What do we call that effect?
Steric hindrance.
Yep. I see it both in the chat and students are mentioning it verbally. Yep. Steric hindrance. Okay. So let's work on any other questions on this first example. Any other questions on this first example? If not, let's work on these next 2. I'm just arbitrarily labeling these positions just so that way we can talk about them in the chat. Which positions will react and which positions will give the major product, which positions are reacted in the minor product. And you can share your responses using the annotate tool verbally or in the chat. And let's work on these examples for about 3 to 4 minutes. Let's try to get a few responses in the chat verbally or annotated on the class whiteboard. And I'd like to see a few student responses before we discuss these examples. So we have one student commenting the nitro group is meta-directing. The isopropyl group is ortho-para. Yep. And they're starting to draw the lines to show how the directing effects link together. Okay, so we have a synergistic set of effects where we have two groups both directing to the same positions. And if we have a choice between reaction at position 1 and position 3, which position will be major? Which position would be major?
Position 3.
Yep, exactly. And it's less hindered. Yep, makes perfect sense. Before we draw out the product, what group are we installing under these conditions? Just to make sure we don't neglect that critical portion. Nitro group, yep. This is electrophilic aromatic nitration. Okay, perfect. So with that established, let's talk through this next example. The nitro group is a meta director. It's a pi acceptor. So it's a very strong directing group. The isopropyl group is an ortho-para director. So they're going to direct to the corresponding ortho and para positions. The nitro group directs to the meta position. We see synergistic additive effects between our two directing groups. And our major product will install the nitro group at the least hindered position, while the minor product will install the nitro group at the slightly more hindered position. What do you mean by is the ring very stable? I'm trying to understand the question. So electron donating and withdrawing groups don't necessarily heavily stabilize or destabilize the aromatic ring. Like we can't necessarily say that this ring is stable, but it certainly, I guess it's best to phrase it in terms of the context. Like in terms of how you can take this ring and subject it to further reactions, it's probably not very reactive to follow up substitution conditions. It is certainly a very electron deficient ring because it has these two nitro groups. But in terms of stability, it's sort of like, what is the context for the stability? Stable towards what kinds of reactions? I mean, it's certainly a deactivated and electron deficient ring. And so it'll be very hard to get like a Friedel-Crafts reaction to occur. But as we'll see later on, electron deficient rings are actually uniquely activated for another class of reaction called nucleophilic aromatic substitution. Does that answer your question? Okay, perfect. So let's look at this last example and let's work through and identify the major and minor products. And we'll discuss this example once I see a few student responses in the chat or verbally. So which of these three positions is most activated for reaction, and where will we observe our major product? Would anyone like to try sharing their proposed annotation, screenshot of the product? One quick correction. the structure drawing tool decided to make this an alcohol, but this is your typical acyl chloride. So you're dealing with traditional Frito-Crafts acylation conditions. Yep, the groups with the oxygen, yep, they're methyl ether derivatives, yep, or you can also call them alkoxide groups or alkoxy groups. Yeah, in this case, we have the methyl ether derivative of our alcohol. We'll talk about naming alcohols next chapter, actually. Keeping focused on the problem, would anyone like to comment which position would we expect to install our acetyl group at?
I have a question. Is it possible with this one for two positions to be like just as strong?
It is a possibility, but in this case, there is clearly a major product and a minor product.
Okay. Thank
Mhm.
you.
So I see some students commenting position 1 and 2, and students really like position 1 as the major. Some students like position 1. What does the rest of the class think? 2. I have some students liking position 2 a little bit more. I see a lot more students commenting about position 2. It is pretty close. It is pretty close. Would anyone care to talk through why? So let's start. This first methyl ether, this first group. This methyl ether, where does it direct? Where does this methyl ether direct?
To position 1.
Yep, it's an ortho-para director. It directs to position 1. We have an exact same methyl ether group. It's directing to positions 3 and 2. And this isopropyl is an ortho-para director, but it's a little weaker. So it directs to position 2 and 3. Position 3 is a no-go due to sterics. And if we had to pick which position 2 or position 1 experiences the greatest amount of directing effects?
Would it be 2 since
2.
Yep. Both of the directing effects are directing to position 2. And so position 2 is slightly more activated. It is a little bit more hindered, but the activating effects do win out in this case because we have a clear difference in activation between our two positions. So this would be the major product, if only slightly. And reaction at position 1 is slightly minor. Does this example make sense to everyone? Any questions on this example? Okay, so let's talk about an alternative way that aromatic rings can react and engage in substitution reactions. In this case, this is nucleophilic aromatic substitution reaction. It's very closely related to the mechanism, for example, for like carbonyl substitution or transesterification. Some reactions that we'll see later on, they follow the same general mechanistic pattern. So aryl halides with electron withdrawing substituents, ortho and para, can react with nucleophiles. The way that this works is we're generating a negatively charged addition intermediate called a Mesenheimer complex that is stabilized by electron withdrawing substituents. Your halide ion, which is ortho or para to your electron withdrawing groups, is lost. And we in turn generate an aromatic ring with our nucleophile installed. So the net process for nucleophilic aromatic substitution is we have replaced our leaving group with a nucleophile. This only works when you have a ring with electron withdrawing groups and many electron withdrawing groups, ortho and para, to your leaving group, ortho and para to your aryl halide. Any questions so far? Okay, so let's talk a little bit about the mechanism for this. First, we have the attack of our nucleophile to generate our anion. This anion is stabilized. We're generating a stabilized anion. So if you have an anion adjacent to a nitro group, you can inherently delocalize and stabilize that anion via resonance, right? Does everyone see how we can take an anion adjacent to a nitro group and stabilize it and delocalize it into our nitro group via resonance? Does that idea make sense? So once we have our stabilized anion generated, the anion then undergoes and then sort of initiates E1CB elimination of our leaving group to regenerate our aromatic ring. This is a textbook E1CB reaction. You may have seen this previously if you have, for example, like a carbonyl with a leaving group at the beta position. You pull off your proton with a base. And once you have your anion generated, that anion, which is resonance stabilized, then kicks down and we lose our leaving group. So this is the textbook E1CB. This is also mentioned in chapter 7 and chapter 8, I believe. And so really the only thing that's new is this first step where we attack our aromatic ring, we break our double bond, we generate a resonance stabilized anion, and then that anion collapses and we eliminate our leaving group following an E1CB mechanism. Now, of course, the only way that this reaction works and proceeds in a product-favored manner is if you have a relatively strong nucleophile and a relatively good leaving group. Does this make sense? So generally good leaving groups are stabilized anions that are generally weak bases and are generally very weak nucleophile. So a good leaving group is a very stabilized anion that is generally a very weak base. Does that answer your question? So generally a generic alkyl halide is the most common substrate in this reaction. Though no fluorine. Fluorine is not a good leaving group. It's a bit abnormal in terms of its electronics. Okay, so when we think about limitations of nucleophilic aromatic substitution, we see that only the ortho and para substituents can stabilize your negative charge, right? So in each of these cases, when our nucleophile attacks and we generate our anion, only the ortho and para nitro compounds actually undergo efficient reaction. The meta nitro compound, no matter how hard we try, this anion cannot be directly delocalized into our nitro group. And as a result, this anion is less stable and it's less likely to form. So your substrate has to have multiple electron withdrawing groups that are ortho or para to your leaving group in order for you to observe efficient reaction. Does this idea make sense? Does everyone see this rationale from a resonance structure perspective? Okay, so let's keep going then. So if you're trying to determine the mechanism of a reaction, the conditions that activate your substrate for electrophilic substitution are fundamentally different than nucleophilic substitution. So under electrophilic substitution conditions, you generally have a stabilized carbocation intermediate, and electrophilic aromatic substitution is favored by electron donating substituents. As a contrast, for nucleophilic substitution, we're stabilizing a carbanion intermediate, or a carbon-centered anion, and nucleophilic aromatic substitution is favored by electron withdrawing substituents. So fundamentally, electrophilic and nucleophilic substitution are two fundamentally different mechanisms with two fundamentally different substrate requirements. Does that contrast make sense to everyone? Okay, so let's talk about another pattern of reactivity of benzene, and this is pretty interesting. It's been subject to a large amount of study. So the way that phenol is prepared on the industrial scale is by treatment of chlorobenzene with aqueous sodium hydroxide at high temperatures. Now, this can't obviously be a nucleophilic aromatic substitution in its traditional form because this benzene ring isn't particularly activated. There aren't any electron withdrawing groups to speak of. So as a result, another intermediate is generated over the course of this reaction, and we call this intermediate benzyne. So in this case, we have our base pulling off a proton and facilitating the elimination of our leaving group. This generates benzyne. This triple bond, it's not a real triple bond. It's very different than a typical triple bond and leads to some very unique patterns of reactivity. I really like to think of benzyne as sort of an anion and a cation on adjacent carbons, as that's very close to how benzyne can react. You can also think of it as a pair of radicals, depending on the exact substrate and the exact reaction that you're using this benzyne intermediate for. So if you have a nucleophile such as water, water will attack your benzyne alkyne, break your triple bond, and then of course you can protonate your anion, and that generates your desired substitution product with your alcohol installed. Now, what's pretty interesting in terms of benzyne is that there's substantial evidence supporting this benzyne intermediate through labeling studies. So bromobenzene with a reactive radioactive carbon label at C1 gives a substitution product with a label at both C1 and C2. So because we see a 50-50 mixture, that is telling us that we are going through an intermediate in which both of our carbon sites are equally reactive. And this supports this idea of a benzyne-like intermediate. Does this idea make sense to everyone? Any questions on this idea? Okay, so benzyne can be used for a range of pretty interesting reactions that we'll bring up later on throughout this semester. Let's talk a little bit about the structure of benzyne. It's a pretty highly distorted alkyne. So when you think about geometry for a moment, having 180 degrees in a 6-membered ring isn't geometrically very easy. It's so you're not getting your traditional alkyne with your traditional alkyne triple bond angle. You're getting more of a distorted alkyne. And in fact, what's pretty interesting is that the triple bond, rather than using p orbitals, actually uses sp2 hybridized carbons rather than the usual sp hybridized carbons. So the triple bond in benzyne has one pi bond formed from p orbital overlap and another pi bond formed by weak sp2 orbital overlap. So your geometry dictates hybridization, and when you have your carbons sp2, you can meet your 120-degree bond angles without breaking your aromatic ring. If you have a formal triple bond which has a 180-degree bond angle, you're sort of out of luck, and you're not gonna really be able to accommodate those bond angles in a 6-membered ring. This sort of unique hybridization and structure of benzyne leads to its very unique patterns of reactivity. Does this make sense? Okay. So another interesting way that we can leverage aromatic structures is the fact that your aromatic ring, even though the actual principal phenyl group or benzene ring in your aromatic system is not very reactive, it's relatively inert to oxidation, the alkyl side chains on the ring can be oxidized up to carboxylic acids, they can be brominated. This benzylic position here is an activated position. And as a result, we can leverage that the benzylic position is particularly activated for a range of oxidation reactions, reduction reactions, and radical chain reactions. So if you have an alkyl group and your carbon that is directly adjacent to your benzene ring is primary or secondary, but not tertiary, you can oxidize up an alkyl benzene to a benzoic acid. Remember, oxidation typically deals with abstraction of a hydride equivalent. So if you have a tertiary position, then there's no H minus to abstract. So a tertiary alkyl side chain won't react. But in cases where you have a primary or secondary alkyl chain, you can oxidize this alkyl chain all the way up to a benzoic acid, cleaving off the remainder of your alkyl chain. It's a relatively niche reaction, but it can have its uses in some cases. Any questions on oxidation of aromatic systems? So the benzylic position is relatively activated. You can oxidize the benzylic position, and you can oxidize this benzylic position all the way up to the carboxylic acid. Any questions on this example? Okay, so let's talk about this other way that we can leverage this very reactive benzylic position. And these benzylic hydrogens in particular are very easy to abstract under radical chain conditions. So a reaction of an alkyl benzene with N-bromoyl succinimide and benzoyl peroxide, that's just our generic radical initiator, introduces bromine into the alkyl side chain. So only one product is observed, and tertiary side chains, again, are not reactive because there's no hydrogen to abstract. So just as a refresher of the mechanism, so you'll start off with your peroxide that we'll draw as ROOR. So under heat or photolysis conditions, you'll generate your first peroxy radical. This is a review of radical chain bromination, but I just wanted to show this mechanism just as a refresher. Your trace amount of bromine that you've generated over the course of this reaction. In this case, the N-bromosuccinimide, it's used as a source and as an equivalent of a trace amount of bromine. And in turn, as you react your radical initiator with bromine, you'll be able to generate an equivalent of bromine radical. Now, this is particularly important because that radical can then go on and abstract a hydrogen that in turn generates our resonance stabilized benzylic radical, especially stable. And then to continue on the chain, our benzylic radical is going to abstract a bromine atom from Br2, and that in turn will generate our final product. If you'd like to review this mechanism in more detail, this is found in the chapter 7 notes from the previous organic chemistry course. So, does everyone notice how because your benzylic radical is especially stable, it's especially easy to generate? So bromination of the benzylic position, or bromination of the benzylic positions in many common alkyl benzene compounds, is quite easy. Does this example make sense? Okay, so let's keep going then. So this is just another overview of the mechanism. So once you've generated your bromine radical, the bromine radical can abstract a hydrogen. You generate a nice stable benzylic radical. Your product, your substrate radical then abstracts a bromine atom from Br2, and we generate our desired brominated product, as well as a second equivalent of bromine radical, allowing you to continue on the radical chain. Okay, the next major idea that's important to bring up is this idea that aromatic compounds and aromatic rings can activate adjacent substituents for reduction. So just like the benzylic positions are especially activated for oxidation, when you connect an alkene or a carbonyl functionality to an aromatic ring, that activates that alkene and carbonyl functionality for further reaction. So the actual aromatic ring is typically inert to catalytic hydrogenation under conditions that normally reduce alkene double bonds. Thus, you can actually selectively reduce an alkene double bond in the side chain of an aromatic ring at room temperature. Neither the benzene ring nor the alkyl ketone is affected. So this shows an example of chemoselectivity, where you don't have to worry that your aromatic ring is going to be reduced under typical alkene reduction conditions. Does this idea make sense? Does this concept make sense? Okay.
Professor,
Yes. Mhm.
I'm not quite sure what's going on in this example.
So these conditions are built up for the hydrogenation of an alkene. So if you take like a typical alkene substrate and you were to subject them to hydrogen palladium in ethanol, you will selectively reduce this alkene by essentially adding an equivalent of H2 across your double bond. Now, when you look at an aromatic ring, you see double bonds present, and the obvious question is then, will the aromatic ring react under hydrogenation conditions? And overwhelmingly, if you're trying to hydrogenate an alkene, you'll almost always be able to selectively hydrogenate the alkene. You'll always be able to selectively reduce the alkene, even in the presence of other functional groups that are potentially sensitive to reduction. Does that explanation make sense?
Yes, thank you.
Okay, perfect. Any other questions that I can answer based on this? Yes, the alkenes in an aromatic ring are particularly stable and they're particularly hard to react. The reduction step would break aromaticity and you pay a pretty huge energetic penalty for that. And we actually saw that when we looked at heat of hydrogenation, right? You don't see nearly as much energy released when you hydrogenate an aromatic ring compared to hydrogenating a typical alkene. And that's part of the fact, partly due to the stability of aromatic systems. Did that answer your question? Yes, yes. If you increase the temperature, pressure, and change the catalyst, you can reduce the aromatic ring eventually, but that requires deliberate conditions. Perfect. Okay, so just like you can potentially activate alkenes for reduction and selectively reduce alkenes, aryl alkyl ketones are particularly activated for reduction. The aromatic ring activates the neighboring carbonyl group towards reduction. So then, the aryl alkyl ketone can be selectively reduced to an alkyl benzene via catalytic hydrogenation. Thus, this sort of completes our complementary methods and ties together this idea that Friedel-Crafts acylation can give us the alkyl ketone via a two-step process. First, we use Friedel-Crafts acylation to generate our aryl ketone, and then we can reduce our aryl ketone to a single alkyl benzene product. So this two-step process of acylation and reduction is very convenient because it allows us to utilize the more selective and slightly more controlled Friedel-Crafts acylation to install alkyl groups. Does that idea make sense? Okay, now another thing to note, and let's talk about this down here, is that acylation installs a meta-directing group that can be utilized as a directing group for future reactions. Thus, by carefully sequencing when you reduce the aryl ketone, it allows you to control the selectivity of substitution reactions for your aromatic ring. So for example, suppose you were tasked to prepare the following compound. It looks easy at first glance because it only has 2 substituents. But if you tried the traditional approach of starting from your alkyl ketone and subjecting it to bromination, well, you'd likely notice pretty quickly that the directing group effects don't direct to the right position, right? Where does this alkyl group direct?
Orthopara.
Yep, it directs orthopara, right? So then you would get the undesired bromination product. So this method is not workable to prepare this target substrate, right? However, if you think about this alkyl group in terms of synthetic equivalence, you can easily utilize a synthetic equivalent of the acyl ketone. And the one benefit of this acyl ketone is that the acyl ketone, by comparison, directs to what position? Where does this acyl ketone direct? Meta, yep. It's a meta-directing group. So even though the alkyl and acyl ketones are synthetically interconvertible, they have different directing group properties, and as such, it may be useful to go through the acyl ketone to get meta substitution patterns. And then of course, you can just reduce off your acyl ketone and you end up with your desired meta disubstituted product. Does this idea make sense? Any questions on this idea? So these reduction steps allow you to interconvert between 2 different functional groups. These functional groups have different directing capacities, and as such, by choosing what group you install and when you time the reduction step, you can get different selectivities. Any questions as we wrap up this chapter? Okay, so that's all I have planned. We finished up with chapter 16.